100 years ago, a deceptively simple formula revealed a hidden unity buried deep in the fabric of the universe. It tells of a fantastic connection between energy, matter, and light. Its author was a youthful Albert Einstein. It's the most famous equation in the world. E equals mc². But while we've all heard of Einstein's big idea, very few of us know what it means. In fact, E equals mc² is so remarkable that even Einstein wasn't sure if it was really true. The gods were not laughing at Einstein. He'd united in one stunning insight the work of many who had come before him. Scientists who'd fought and even died to create each part of the equation. The story of E equals mc² starts long before Einstein with the discovery of E for energy. In the early 19th century, scientists didn't think in terms of energy. They thought in terms of individual powers or forces. These were all disconnected, unrelated things. The power of the wind, the force of a door closing, the crack of lightning. The idea that there might be some sort of overarching, unifying energy which lay behind all these forces had yet to be revealed. One lowly man's drive to understand the hidden mysteries of nature would begin to change all that.
Young Michael Faraday hated his job. He was uneducated, the son of a blacksmith. He'd been lucky to become a bookbinder's apprentice. But Faraday craved one thing. He craved knowledge. He read every book that passed through his hands. He developed a passion for science. All of his free time and his meager wages were poured into his self-education. He was on the threshold of an incredible journey into the invisible world of energy.
Faraday had impressed one of his master's customers and was rewarded with a ticket that would change his life.
Excuse me, please. Can I pass, please?
Can I pass?
Some of us are trying to improve ourselves. If people will let us.
Of course, of course. Pass, pass. This way to a better life.
In the early 1800s, science was a pursuit of gentlemen, something Faraday was clearly not. He had a rudimentary education, he'd read widely, he'd gone to public lectures. But in 1812, he was given tickets to hear Sir Humphrey Davy, the most prominent chemist of the age.
19th century scientists were the pop stars of their day. Their lectures were hugely popular. Tickets were hard to come by, and Davy reveled in his status.
They're waiting.
I know.
He was also a keen follower of the latest fashion, nitrous oxide or laughing gas. He said it had all the benefits of alcohol without the hangover.
Electricity, ladies and gentlemen. A mysterious force that can unravel the confusing mixture of intermingled substances that surround us and produce pure elements.
Davy was an absolutely first-rate scientist. However, Many will come to say that his greatest discovery is Michael Faraday.
Metals unknown, that is, until I isolated potassium from molten potash and sodium, as I showed you last time, from common salt. That same magical
Faraday may not have been born a gentleman, but he wasn't going to let class barriers stop him from pursuing a career in science. He worked for nights on end to bind his lecture notes into a book for his new hero.
Lord, help me to think only of others, to be of use to mankind. Help me be part of the great circle that is your work and love. Lord, I am your servant.
Well, this is excellent work, Faraday. So what is it you aim to do with your life?
My desire, sir, is to escape from trade, which I find vicious and selfish, and to become a servant of science, which I imagine makes its pursuers amiable and liberal.
Really? Well, I shall leave it to the experience of a few years to set you right on that score. Look, I haven't anything at the moment. I'll send a note if anything comes up.
Despite this humiliating setback, Faraday was determined to break free from his daily toil. His patience was rewarded.
You man, meet Mr. Michael Faraday. He's going to be my helper while I recover. He assures me he is a Christian fellow. Perhaps with God and Faraday in charge of the chemicals, you and I will be safe in our place of work.
Thank you, Professor Davy. Welcome, Faraday.
Oh, no, thank you, and thank you, Sir Humphrey.
Just stick to your job and do as you're told, and you'll be fine, Faraday.
Faraday became the laboratory assistant, eagerly absorbing every scrap of knowledge that Davy deigned to impart. But in time, the pupil would surpass the master. The big excitement of the day was electricity.
Another charge, Newman.
The battery had just been invented, and all manner of experiments were being done. But no one really understood what this strange force of electricity was.
The academic establishment at the time thought that electricity was, like a fluid flowing through a pipe, pushing its way along. But in 1821, a Danish researcher showed that when you pass an electrical current through a wire and place a compass near it, it deflected the needle at right angles.
This was the first time researchers had seen electricity affect a magnet, the first glimpse of two forces which had previously been seen as entirely separate, now unified in some inexplicable way.
Faraday, come look at this. You're the bright spark around here. Perhaps you can work it out. Ersted's reported an amazing finding. We're just replicating it here.
Let's try the compass on the other side.
Now, that is remarkable.
But if the electrical force is flowing through the wire, why does the needle not move in the same direction, parallel to the wire?
Quite.
Let's try turning the whole apparatus round.
Again, Newman.
So, the electrical force goes this way. The compass points that way. How can one affect the other?
Perhaps the electricity is throwing out some invisible force as it moves along.
What?
Perhaps some sort of electrical force is emanating outwards from the wire.
Oh, my dear boy, let me tell you that at the University of Cambridge, electricity flows through a wire, not sideways to it.
Well, that may be what they teach at Cambridge, but it doesn't explain what's happening before our eyes.
No, let's just get on. Let's swap the compass to below the wire.
Why the compass was deflected at right angles, why the electricity was affecting the compass at all, dumbfounded Davy and many others.
As we celebrate the marriage of Michael and Sarah.
For Faraday, however, the problem became an obsession. It was a fascination inspired by his religion. For him, the problem was a way to understand God's hidden mysteries.
A love for our fellow man.
There was a small, almost persecuted group in London called the Sandemanians. They were religious, not really a sect. They were just a small subset, sort of like Quakers. Faraday was a member of that group. It was a very gentle, decent group. They believed that underneath the whole surface of reality, everything was created by God in a unified way, that if you opened up one little part of it, you could see how everything was connected.
Michael Faraday was someone who, like Einstein, thought in terms of pictures.
Faraday was different from anybody else. He had a flair for understanding his experiments, for understanding what was really going on inside them.
By methodically placing a compass all around an electrified wire, Faraday started to notice a pattern.
What everyone else at the time had been taught was that forces travel in straight lines. Faraday was different. Faraday imagined that invisible lines of force flowed around an electric wire. And then he imagined that a magnet had similar lines emerging from it, and that those lines would get caught up in this flow. It was a bit like a flag in a wind.
But Faraday's great leap of imagination was to turn this experiment on its head. Instead of an electrified wire moving a compass needle, he wondered if he could get a static magnet to move a wire.
I've never seen you like this, Faraday. You look like a happy child.
I'm shaking, Newman. Underneath, I'm shaking. You see, John? You see?
Yes.
This is the experiment of the century. It's the invention of the electric motor. Scale up the magnets and the wires, make them really big. Attach heavy weights to them, and they'll be dragged along. But almost more importantly, he's inventing a new kind of physics here.
Although he didn't realize it at the time, Faraday had also just demonstrated an overarching principle. The chemicals in the battery had been transformed into electricity in the wire, which had combined with the magnet to produce motion. Behind all these various forces, there was a common energy.
A couple of months earlier, Davy had been elected president of the Royal Society, which was the elite body of English science. But then he saw this great discovery published in the Quarterly Journal of Science. I don't know if he was envious, but he certainly saw that this young man who had been his assistant, this mere blacksmith's son, had come up with one of the greatest discoveries of the Victorian era.
Davy accuses Faraday of plagiarizing similar work from another eminent British scientist, William Wollaston.
So, Faraday, what does Wollaston make of all this?
He's written to me and assures me that he's taken no offense. And he acknowledges that what I published was entirely my own work.
Right. Davy is just being an ass.
But will Davy now retract his allegation?
Sadly, no. In fact, he's still vehemently opposed to you being elected a member of the Society.
Really? And what do you think?
Faraday, my dear boy, you have my vote.
And mine. And I believe you even have Wollaston's.
Oh. What a mess.
Well, no matter. No matter. It's the science that counts. So tell me, how does this wire of yours spin round its magnet? What mysterious forces are at play?
There seems to be an electromagnetic interaction. In my mind, I see a swirling array of lines of force spinning out of the electrified wire, like a spiraling web.
But invisible lines of force, it's all a bit vague, isn't it?
Faraday, might I have a word in private?
Certainly.
Listen, Faraday, let's stop this nonsense. I want you to take down your ballot paper from the notice board.
Sir Humphrey, I see no reason to take it down. My friends have proposed me. It is they who put the paper up. I will not take it down. Good day.
Faraday was elected to the Royal Society. Davy died 5 years later, a victim of his many gaseous inhalations. In time, Faraday's world of invisible forces would lead to a whole new understanding of energy. He'd started what Einstein would call the Great Revolution. It was in the very heart of this exciting new world of energy that Einstein grew up.
My father and uncle wanted to make their fortune by bringing electric light to the streets of Germany. From an early age, I loved to look at machines, understand how things work.
He's going to kill himself. Albert, stay there.
I experienced a miracle when my father showed me a compass. I trembled and grew cold. There had to be something behind objects that lay deeply hidden. At high school, they had their ideas about what I should learn. I had my own. I was merely interested in physics, maths, philosophy, and playing the violin. Everything else was a bore.
Einstein! On your feet! As you obviously know everything about geology, tell me, how does a rock start run here?
It's pretty much the same to me whichever way they run, Herr Professor.
Einstein's teachers tried to drum into him, as Faraday had shown, that energy could be converted from one form into another. They also believed that all forms of energy had already been discovered. Einstein was going to prove them wrong. He would discover a new, vast reservoir of energy hidden where no other scientist had ever thought of looking. Deep in the heart of matter. 100 years before Einstein's birth, King Louis XV was on the throne of France. But the ancient absolute power of the monarchy over the people was starting to be challenged.
Jacques, leave the windows. Forget the rain. We need air.
The French Revolution was just around the corner.
This was the era of enlightenment, when intellectuals believed very firmly that the way forward lay in science. And they felt that one of the first tasks that lay ahead of them was to rationalize and to classify every single kind of matter so they could see how it all interacted together.
Antoine Lavoisier, a wealthy, aristocratic young man, decided to take up this task, to see if there was some basic connection between all the stuff of everyday life, all the different substances in the world. But what worked for Lavoisier as a scientist, his meticulous, even obsessive attention to detail, was also to be his downfall.
Monsieur Lavoisier, you are, if my eyes do not deceive me, consuming only milk this evening. First you had a glass of milk, now you are eating a bowl of milk. Will you next move on to a plate of milk?
Your precise observations commend you as a lady of scientific curiosity, mademoiselle. Most unusual. As you seek knowledge, so I shall dispense it. For the last 5 weeks, I have taken nothing but milk.
Good God, man. I would rather die than fast on milk for 5 weeks. Are you in the grip of some horrendous ailment?
On the contrary, I am investigating the effects of diet on health.
Monsieur, with the greatest of respect to a member of the Royal Academy of Sciences, your gut must think your throat has been slit.
Whereas your gut, Count, is no doubt petitioning the Academy for a widening of your throat.
Marianne, how dare you insult the Count?
Lavoisier wasn't a scientist by profession. He was the head of tax enforcement in Paris. His great idea was to build a huge wall round the city and to tax everything that came and went. But his taxes on the simple things in life, bread, wine, and cheese, did not endear him to the average Parisian. This scrupulous, fastidious young man did still allow himself the occasional act of passion. Marianne learned chemistry at her husband's side, but soon sought other ways to contribute to his work. She learned English so that she could translate contemporary scientific works. She took drawing lessons so that she could record in forensic detail the minutiae of their work together. She ran their laboratory and was the public face of Lavoisier, Inc. She was central to the whole research effort.
That is a terrible thing to say. You are a cheeky man.
This way, please, gentlemen. Monsieur, it is my great ambition to demonstrate that nature is a closed system. That in any transformation, no amount of matter, no mass, is ever lost, and none is gained. Over here, please. This precise amount of water is heated to steam. This steam is brought into contact with a red-hot iron barrel embedded in the coals. From this end, we cool the steam. But interestingly, we collect less water than we started with. So clearly, we lose a certain amount of water. However, we also collect a gas. And the weight of the iron barrel increases. Now, when we combine these two increases, the new weight of the iron barrel and the gas we have collected, they are exactly equal to the weight of the lost water.
Ah, but is it atmospheric air, Monsieur Lavoisier?
No. No, because I am measuring it to the very last grain. I can see that it is lighter than the air around us. And, moreover, it is flammable. Voila.
Water is made out of hydrogen and oxygen. So what he had done is get the oxygen to stick to the inside of a red-hot iron rifle barrel. He was basically just making rust, which is oxygen and iron, but he was making the rust really quickly. Now that left the hydrogen, what he called combustible air, and that was just floating around as a gas. No mass had been lost, it had merely been transformed. And now he wanted to transform it all back into water.
This is only the beginning. In the next few months, I hope to demonstrate that I can recombine this combustible air with vital air and transform them both back into water. I will recreate exactly the same amount of water that was lost here in this process. It is my hope to complete the cycle, water into gas, into water, and not a drop lost.
For a long time, Lavoisier had suspected that the exact amount of matter, the mass, involved in any transformation was always conserved. But to prove this, he had to perform thousands of experiments, and he had to do the measurements with incredible accuracy. That's where his great wealth from being a tax collector came in. He could afford to commission the most sensitive instruments ever built. He became obsessed with accuracy.
But Lavoisier's exacting methods were also starting to anger the growing mob of hungry, disenchanted Parisians.
Antoine? Antoine? Oh, wake up, Antoine!
I'm sorry. What time is it?
It is almost time to receive Monsieur Marat. The Academy asks you to assess his designs. He claims to have made a great discovery. Oh, Antoine, have you forgotten?
There's another charlatan with an idea to peddle. God give me patience. Monsieur Marat.
Monsieur, I have invented a device which projects an image of the substance of fire onto a screen. You see? When a lantern is shone through a flame, we see a shimmering pattern above the flame. My device renders the substance of fire visible.
Have you collected it, this substance of fire? Have you trapped it and measured it?
Oh, no, but one can see it.
I'm sorry, in the absence of exact measurements, of precise observations, without rigorous reasoning, one can only be engaging in conjecture, so this is not science.
I am not given to conjecture, monsieur.
Really, no. If you will excuse me, I am extremely busy today, but thank you. Thank you.
So that is all? Then good day, monsieur!
Let me guess, Marat. The King's scientific despot has decreed that your invention does not conform to the version of the truth as laid down by the Academy.
Lavoisier. He talks about facts. He worships the truth.
Listen to me, my friend. They are all the same, the Royal Academies. They insult the liberty of the mind.
They think they are the sole arbiters of genius. They are rotten to the core, just like every other tentacle of the king. The people. It is they who will determine right and wrong.
Don't worry. In my next pamphlet, I will expose this persecutor of yours.
For years, the Lavoisiers burned, chopped, melted, and boiled every conceivable substance. They'd shown that as long as one is scrupulous about collecting all the vapors, liquids, and powders created in a transformation, then mass is not decreased. Liquids might become gases, metals may rust, wood may become ash and smoke, but matter, the tiny atoms that make up all substances, none of it is ever lost. The crowning glory of this opus was their remarkable use of static electricity to cause oxygen and hydrogen to recombine back into water.
What is happening?
As the French Revolution exploded, the royal family and whole swaths of aristocrats lost their heads on the guillotine.
To the French revolutionaries of 1790, Lavoisier meant one thing and one thing only. He was the despised tax collector who'd built that wall around Paris.
Lavoisier's job as a tax collector brought him under suspicion. He was denounced by a failed scientist turned radical journalist, Jean-Paul Marat.
Où est Lavoisier?
Je sais pas.
Lavoisier! Lavoisier! Lavoisier!
What Lavoisier did is absolutely central to science and especially T equals mc². Because what he said is if you take a bunch of matter, you can break it apart, you can recombine it, you can do anything to it, and the stuff of the matter won't go away. If the mob burned Paris to the ground, utterly razed it, shattered the bricks into rubble and dust, and burned the buildings into ashes and smoke, turns out if you put a huge dome over Paris and weighed all the smoke and all the ashes and all the rubble, it would add up to the exact same weight as the original city and the air around it before. Nothing disappears.
A century later, all of nature had been classified into two great domains. There was energy, the forces that animated objects, and there was mass, the physical stuff that made up those objects. The whole of 19th century science rested on these two mighty pillars. The laws that governed one did not apply to the other. But young, newly enrolled physics student Albert Einstein didn't like laws.
But Cliff, Einstein,
What happened to you?
It is more than a little ironic, having been reprimanded yesterday by that idiot Professor Pernay for poor attendance, that I should in fact attend a practical lesson, which was as long as it was boring and utterly pointless, by the way, only to be the victim of an explosion of my own apparatus.
So it was your own fault then?
Thank you. And how are you today, Fräulein Marriage?
Extremely well, Herr Einstein. All the better for seeing you have escaped the physics laboratory with your life.
Well, in order not to alarm you any further, I pledge to forever continue my studies here at the Café Bahnhof, reading only the great masters of theoretical physics and eschewing the babbling nonsense of the polytechnicians.
It's about all you ever do.
It's getting a little stuffy in here, Fräulein Marriage. Would you care to take a walk with me? There's something I'd like to discuss with you.
Why, Herr Einstein? Of course. Perhaps you'd like me to tell you what you have missed in lectures this week.
Einstein wasn't exactly a model student. He excelled in certain subjects, especially physics and math, but he wasn't very diligent in a lot of his other classes. He was undoubtedly very questioning, which seems to have annoyed most of his professors throughout his life. He would pursue his fascinations with just incredible determination.
We know from his letters that Einstein, even from the age of 16, was literally obsessed with the nature of light. Everyone he could speak to, his friends, his colleagues, even his then girlfriend, Mileva Merrick, who would become his wife, everyone he badgered with the question, what is light?
What would I see if I rode on a beam of light?
What? A beam of light? By what method do you propose to ride on this beam of light?
The method is not important. Let us just imagine we two are young, radical, bohemian experimenters, hand in hand on a journey to the outer reaches of the universe, and we are riding on the front of a wave of light.
I really don't know what you are suggesting, Herr Einstein. Do you wish to hold my hand or ridicule me?
Ridicule you? No, never. I merely want you to help me to understand. What would we seize, you think, if we were together and we sped up and up until we caught up to the front of a beam of light?
It was Einstein's relentless pursuit of light which would bring about a revolution in science. With light, he would reinvent the universe and find a hidden pathway that would unite energy and mass. Light moves incredibly fast, 670 million miles per hour. That's why scientists use the term c. It stands for celeritas, Latin for swiftness. Long before the 19th century, scientists had computed the speed of light, but no one knew what light actually was. Back in England, a man we've already met was willing to make an educated guess. After Sir Humphrey Davy's death, Michael Faraday became Professor Faraday, one of the most important experimenters in the world. The scientific establishment still found it hard to accept that electricity and magnetism were just two aspects of the same phenomenon, which Faraday called electromagnetism. But now, he has an even more outrageous proposal for his audience.
Invisible lines that can emanate from electricity in a wire from a magnet, or even from the sun. For it is my contention that light itself is just one form of these vibrating lines of electromagnetism.
For 15 years, Faraday struggled to convince the skeptics that light was an electromagnetic wave, but he lacked the advanced mathematics to back up his idea. Eventually, someone came to his rescue. Professor James Clerk Maxwell believed in Faraday's far-sighted vision, and he had the mathematical skill to prove it. Maxwell and the aging Faraday became close friends.
James, forgive me. A word of advice. Don't get old.
Michael, how are you?
I'm fine. Memory isn't too good. But...
Well, I thought you might like to see what I've just published.
Oh, yes. Yes. Splendid.
So your results show that when electricity flows along a wire, what it actually does is create a little bit of magnetism. And as that magnetic charge moves, it creates a little piece of electricity.
Electricity?
Electricity and magnetism are interwoven, like a never-ending braid. So it is always pulsing forward.
It's wonderful.
Michael, there's something very crucial in the maths. This electricity producing magnetism and magnetism producing electricity, it can only ever happen at a very particular speed. The equations are very clear about it. They come up with just one number. 670 million miles per hour.
I'm not sure.
It's the speed of light. That is the speed of light. You were right all along. Light is an electromagnetic wave.
Maxwell had proven Faraday right. Electricity and magnetism are just two aspects of a deeper unity. A force now called electromagnetism, which travels at 670 million miles per hour. In its visible form, it is nothing other than light itself. And nothing fascinated the young Einstein more than light.
Maxwell's equations contained an incredible prediction. They said you could never catch up to a beam of light. Even if you were traveling at 670 million miles an hour, you would still see light squiggle away from you at 670 million miles an hour.
Do you see how she stares at that wave?
Yes.
You see how for her it is static?
Yes.
She and the wave are traveling at the same speed. We see the wave moving through the water, but relative to her, it just sits there. So is light like that?
Common sense would say that if you caught up to a light beam, there would be a wave of light just sitting there. Maybe it would be shimmering, a bit of electricity and a bit of magnetism.
So, if she was traveling alongside the light wave, it wouldn't be moving, it would be static. But Maxwell says you can't have static light.
Maybe Maxwell is wrong. Maybe if you catch up to light, it is static, Albert, like a wave next to a boat.
Imagine if I was sitting still and holding a mirror to my face. And the light travels from my face to the mirror, and I see my face.
Yes.
However, if I and the mirror were traveling at the speed of light...
You're going at the same speed as the light leaving your face.
Exactly.
The light never reaches the mirror.
So would I be invisible?
That doesn't make sense.
Young Einstein was starting to realize that light was unlike any other kind of wave. Einstein was about to enter a surreal universe where energy, mass, and the speed of light intermingled in a way no one had ever suspected.